Good morning, students. We begin with our today's session. In yesterday's lectures, we completed serial communication. Today we will go for interrupts. In this session, we will look into interrupts, the special function registers associated with interrupts, how is the internal interrupt structure, okay, and related to interrupt, we will see LED blinking using internal timer interrupt. So let us begin with. So 8051 microcontroller provides total 5 interrupts, right? So there are total 5 interrupts, out of which 2 are the hardware interrupts, INT0 bar and INT1 bar. The external pins P3.2 and P3.3, that is INT0 bar. See, there is a slash mentioned. So that is indicating INT0 bar, active low hardware interrupt. INT1 bar, active low hardware interrupt. So these are the two external hardware interrupts and they are active low. And the remaining 3 are the interrupts which are generated internally by timer 0 interrupt, timer 1 and the serial communication. So the remaining 3 interrupts are generated internally by the respective peripherals, timer 0, timer 1 and serial communication. Now see, in serial communication, we have transmission as well as reception. But for transmission and reception, there is a single interrupt which is called as serial communication interrupt. Correct? So timer 0, there is a separate one. Timer 1, there is a separate interrupt. But for serial communication, transmission and reception, there is only one serial interrupt. Okay. So altogether 5 interrupts. Right? And all these interrupts are vectored interrupts. They have the priority and the priority can be changed. So vectored mean whenever, see, what is an interrupt mechanism? Interrupt, from the name itself, microcontroller is doing some certain operation. When an interrupt arrives, it stops the current operation, jumps to some another location to execute another program, and then it returns back. So that is, it's interrupting microcontroller from doing the original thing. Right? Now, where to jump? What does microcontroller do? It knows from what address the instructions are to be executed. Correct? Microcontroller always knows. It depends on the contents of program counter. So depending on the address in program counter, microcontroller executes those particular instructions. So when an interrupt arrives, program counter gets loaded with some definite address. And hence, on interrupting, microcontroller jumps to that particular fixed address, executes the program from that address and returns back. So that's called vectored. When an interrupt arrives, which instruction is to be executed is known to microcontroller. Correct? Hence the name vectored. So 8051 has 5 interrupts and all the 5 interrupts are vectored interrupts. Is that okay? I think so. In 8086 microcontroller, students, do you all remember something like this? Vectored interrupts and non-vectored interrupts? 8086 microprocessor. In 8086 microprocessor, there was one non-maskable interrupt and there was one maskable interrupt. Non-maskable was NMI and the other was INTR. And these were the 2 hardware interrupts. And the remaining interrupts were software interrupts, 256 software interrupts. Okay. So INTR interrupt was non-vectored, if I remember it correctly. When non-vectored interrupt means what? When an interrupt arrives, microcontroller on its own does not understand where to go. Programmer has to write a program to tell microprocessor where to jump. That is called non-vectored. Right? Vectored means microcontroller automatically one fixed address will be loaded in program counter and microcontroller jumps automatically. Right? That is vectored. And non-vectored means with the help of instruction, we load program counter, and then microcontroller jumps to the vector address. Now, in our case, all the 5 interrupts in 8051 microcontroller are vectored interrupts. Automatically, a fixed address gets loaded in program counter and microcontroller jumps to that fixed address for further execution. Okay. And the another feature is all the interrupts have a priority. There is a fixed priority to all the interrupts. Now, why do you need priority? Priority is useful when multiple requests occur at the same time. That is where that priority helps, right? So we have 5 interrupts. All the 5 interrupts, if they arrive to microcontroller at the same time, microcontroller should resolve that and execute one interrupt. So that is done. Multiple requests occurring at the same time is resolved with the help of priority. The interrupt which has the highest priority will be serviced by microcontroller, right? So that is what is priority. Priority can also be changed with the help of IP register, interrupt priority register. Is that okay? Now, so all the interrupts are vectored and they have a fixed priority as well as the priority can be changed. Okay. Now, what are these interrupts, right? These interrupts help microcontroller to perform multitasking. Multitasking means multiple operations handled at a time. It is for this purpose there are interrupts to any microprocessor or any microcontroller. Okay, so that is for the purpose of multitasking. Now, multitasking, if you actually see what microcontroller does one task at a time. So that multitasking is like illusion of doing things simultaneously. For human being, it appears as if all the things are happening simultaneously. But for microcontroller, it will handle one task at a time. Right? So suppose there are 4 operations going on. Right? What are the 4 operations? Taking character from the keyboard, displaying something on the LCD, sensing temperature of a certain device. Right? For human beings, it appears as if microcontroller is doing all the things simultaneously at a time, but that is not so. Microcontroller will be doing one thing at a time, either displaying on the LCD or sensing the temperature. But this one after the other happens so fast, correct? The operating frequency of microprocessors is in megahertz. So one after the other, the things happen so fast that for us it appears all the things are looked after by the microcontroller at the same time. So that multitasking is as if for us it is actually it's illusion of doing things simultaneously. Hope you get me. But multiple operations can be handled by interrupts. More the interrupts to a particular microcontroller, it is possible to do more multitasking with the help of that microcontroller, right? Now, what does this interrupt do? As I said, on an occurrence of an event, on the arrival of that interrupt, microcontroller will stop the main program execution, jumps to execute a program which we'll be calling it as interrupt service routine, ISR, or interrupt subroutine. So on arrival of interrupt, microcontroller will stop the main program execution, jump to ISR, execute the ISR, and return back to the main program. So this is what happens on arrival of interrupt. Is that okay? Now, a little bit better understanding. So how does the main program and the interrupt subroutine interaction happens? Is that okay? We will see to it, right? On arrival of interrupt, what all operations happen internally inside the microcontroller, we will see to it. Okay, so the interaction between main program and the ISR. Now main program, the program which begins from 000 hex is the main program. And the main program is such that it is whenever you all do your projects, the main microcontroller will always keep on executing the main program. So it is in an unconditional, unending loop. Correct? Whatever project we do, that project should run 24/7. So that main program is always in a while loop, unconditional, never-ending loop. And the program is the one which begins with 000 hex. So for example, I have written some program here at 00 hex, MOV A, 12, at 100 location, there is ADD A, so some program has been written indicating that's a main program. Correct? And now suppose microcontroller is continuously busy in executing the main program, and when it is executing the instruction at 100 hex, suppose an interrupt arrives. Suppose INT1 interrupt arrives. Right? So while executing ADD A, @R0, right, the main program instruction, INT1 external hardware interrupt arrives. Then what does microcontroller do? It first finds out the return address which is to be stored on stack. So what is the return address? The address of the instruction immediately next. So ADD A, R0 was written at 100. The next instruction address will be at 101. This is ADD is a 1-byte instruction. So the first thing microcontroller does is finds out the return address. That's the address of the next instruction. Saves this return address on stack. Mean 0101. This address is saved on stack. Then it jumps to the ISR, interrupt service routine. Mean which interrupt had arrived? INT1. So there is a vector address allotted to INT1. And that vector address is 00B. So after saving the return address on stack, microcontroller automatically jumps to 000B. That's the vector address of INT1. Correct? So jumps to the vector address of interrupt subroutine, executes. Yeah. Now on entering the ISR, all the interrupts are disabled. Right? So whenever microcontroller executes any of an ISR, it jumps to the ISR and disables all the interrupts. Then executes the ISR. And the end instruction of ISR is interrupt return, IRET. On execution of interrupt return, all the interrupts get enabled and the return address on stack is popped and stored in program counter. And that's how it returns to the main program. That okay? So the last instruction of ISR should always be interrupt return, IRET. Why? Right? You have two RET instruction and this one is IRET instruction. So what does IRET instruction do? It enables all the interrupts and pops the return address in program counter. And hence the name of the instruction is return, RET. And that's how it returns to the main program. So where does it return to? 0101 instruction. It executes INC R0. Okay. So when it returns to the main program, microcontroller will execute the main program and will remain in the loop. That's how it's an interaction between the main program and the ISR. Are you getting me? See, can you find this? The same operation we had seen earlier also. Yes or no? The interaction between the main program and the subroutine. When did we see this, students? When we studied call instructions. Call instruction, what it does? Call instruction, it stops the current execution, jumps to the subroutine, executes the subroutine and returns back to the main program. So this interaction we had seen before while studying call instruction. What are we studying now? We are studying interrupts. Right? So interrupt and call, there is a similarity. What does interrupt do? On arrival of the interrupt, it stops the current execution. Microcontroller stops the current execution, saves the return address on stack, jumps to the vector address of the interrupt, disables all the interrupts, executes the ISR, interrupt subroutine. On execution of interrupt return instruction, enables all the interrupts and returns back to the main program. So that's how that main program and the interrupt interact with each other. So now, so I have shown here how is the time frame for execution of main program by the microcontroller when an interrupt arrives. That figure B shows the time frame for execution on arrival of the interrupt, and figure A the time frame for execution when there are no interrupts. Correct. So what did I say in the earlier example? Microcontroller is always busy in executing the main program. So look into figure A. With respect to time, microcontroller keeps on sequentially executing the main program. One instruction after the other, then the next instruction, then the next. And this process is continuous. So the diagram A is a time frame when there are no interrupts arriving. But look into figure B. Microcontroller is executing the main program. Start from the left hand side. So initial time, microcontroller is executing the main program. On arrival of interrupts, it stops the execution of the main program, jumps to ISR, executes the ISR, and on I return instruction comes back to the main program. Right? Executes the further main program. See here, executes the further main program. Again, on arrival of another interrupt, jumps to ISR, executes the ISR, returns back to the main program. Continues with the execution of main program. Again, on arrival of interrupt, next, and next. So that's the time frame when interrupts arrive. Right? Figure B. One more point to understand in this is, see, whenever interrupt subroutine is being executed, all the interrupts are disabled automatically. Correct? It means unless and until the interrupt program does not get executed, further new interrupts will not be accepted by microcontroller. Why? Because automatically all the interrupts are disabled on execution of ISR. Right? So there is a term called nested interrupts. What is nested interrupt? While executing the main program, interrupt 1 arrived. So microcontroller jumped to interrupt 1 ISR. While executing the ISR, if another interrupt arrives, that is also accepted. And from one ISR, microcontroller jumps to a second ISR. Correct? So interrupt within an interrupt is called nested interrupts. Is that okay? But in case of microcontroller, when an ISR is executed, automatically all the interrupts are disabled. Correct? Normally nested interrupts are not allowed in 8051 microcontroller. So by default, nested interrupts are not allowed. Go to one ISR, complete the ISR execution, return back to the main program, and then accept a new interrupt. Correct? But we can change this. Right? We can make nested interrupts. How can we do that? Whenever we jump into ISR, I will write an instruction to enable the interrupt. By default, the interrupts are disabled. No problem. I will write an instruction. I will again enable the interrupts in the ISR. And now microcontroller is ready to receive another interrupt in the ISR. So nested interrupts is possible provided the programmer writes an instruction to enable the interrupts. By default, when an ISR is executed, the interrupts are disabled. But the programmer can enable it and have the facility of nested interrupts. Right? Now the diagram which is shown here, this is not a nested interrupts. From the main program, go to ISR, complete the ISR execution, return to the main program. Second interrupt, complete the ISR execution, return to the main program. So this is not a nested interrupts. Fine. And by default, this is how microcontroller behaves. But we can change the behavior and make it nested. Now next. So I told you all there are altogether 5 interrupts and all the 5 interrupts are vectored. Right? Vectored means microcontroller on arrival of that interrupt, microcontroller will jump to one fixed address in program memory. So let us look into the vector addresses of all those 5 interrupts. So I've shown here a table. I've mentioned the vector address of that particular interrupt. I have shown the priority, whether that interrupt has arrived or not, mean that particular flag bit is also shown. Okay, and these flag bits are available in which SFR is also shown. I'm going to show you the flag bit, the vector address of that particular interrupt, what is the priority, and where are these interrupts available. Those 5 interrupts, INT0, INT1 bar are the hardware interrupts. Timer 0, timer 1 and serial communication are the internal hardware interrupts, internally generated hardware interrupts. Whether the particular interrupt has occurred or not, that information the programmer can see. So whether int0 hardware interrupt is arrived or not, the programmer can keep on checking that IE0 bit. Correct? Whether the timer interrupt has arrived or not, it can keep on checking. The programmer can check TF0 bit. Okay. Or the other way to understand, when an int0 interrupt arrives, IE0 bit is set. Interrupt enable 0 bit is set. When timer 0 interrupt arrives, TF0 flag is set. Correct? INT1 interrupt, IE1 flag is set. Timer 1 interrupt, TF1 flag is set. And for serial communication, either the RI flag is set or the TI flag is set. RI stands for receiver interrupt, TI stands for transmitter interrupt. So any time when these flag bits are set, that's an indication of arrival of an interrupt. Correct? IE0 indicates int0 interrupt has arrived. TF0 timer 0 interrupt has arrived. IE1 int1 interrupt has arrived. TF1 timer 1 interrupt has arrived. RITI serial communication interrupt has arrived. So these are the corresponding flag bits and we have seen all of them. Correct? With the help of instruction, we were looking jump JNB, jump if the bit is not set. And we were checking all these flags. But what were we doing? We were not using interrupts. With the help of instruction, we were checking this. So that is what we were doing, polling technique to understand whether the operation is over or not. Okay. JNB, writing an instruction and checking the flag. That is called polling technique. But what are we studying now? Interrupt. Microcontroller need not keep on checking whether interrupt has arrived or not. Microcontroller will keep on executing the main program and that interrupt will automatically be generated and it will be interrupting the microcontroller. Okay. In the earlier case, JNB, jump if the bit is not set. Polling technique. Microcontroller is continuously busy checking the flag. It cannot do anything else. That is called polling. What are we studying now? Interrupts. Where the multitasking is possible. Microcontroller can do some other execution, whereas the other operation, when it is completed, will generate an interrupt. When a timer can keep on working in the background, and when the timer 1 millisecond delay is over, it can interrupt the microcontroller. Microcontroller need not wait till 1 millisecond is over. It can do something else. Okay. Now, what are the vector addresses? int0, the vector address is 0003. These are the addresses of program memory. Okay. So the vector address of int0, 3, timer 0, B, int1, 13 hex, timer 1, 1B hex, and serial communication 2-3 hex. So these are the addresses automatically loaded in program counter, and hence microcontroller starts executing the instructions written at those particular address. So when int0 arrives, microcontroller will automatically start executing instruction written at 3 hex. Okay, as I did show an example here. When int1 arrives, microcontroller will automatically start executing instruction written at that address B. Right? Why? Because these are vectored interrupts. So it is easy to remember the addresses 3B, 131B and 23. Okay, students. Right? Now see here, students, if I look into those addresses, right, I had told you all earlier also, 3 of how many locations far is that letter B? So 3, 4, 5, 6, 7, 8, 9, A, B. So just a gap of 8 memory locations, and I have the vector address for the another interrupt, timer 0. After B, another 8 memory locations, we have a vector address of int1. Right? Mean the gap between the vector addresses is hardly 8 memory locations. Okay. So it becomes difficult to fit this ISR in just within those 8 locations. Okay. So then what we generally do is, see here, what we generally do is, even if microcontroller automatically jumps to the vector address, right, we modify this. Instead of writing here, what do? We just write one jump instruction. Okay, what do we do here? We will be writing LJMP and let that label be ISR1. So that's the label and the instruction is LJump. Or we will be writing, I can also write LCall ISR1. And where is my actual program written? My actual program is written at ISR1. That's the label. Is that okay? So this is how we manage with that, since we have lesser space in between the consecutive vector addresses. This is how we modify it. Right? So usually what is done? No doubt when an interrupt arrives, microcontroller finds the return address, saves the return address on stack, jumps to the mentioned vector address, and at that vector address, whenever it jumps to the vector address, it disables all the interrupts, and at that vector address we write jump again to somewhere else. Either write a long jump instruction or write a long call instruction. So jump somewhere else. Right? So we preferably use ljump to some label, and at that label we write the subroutine, we write the ISR. Correct? It executes the when it jumps, it disables the interrupt, and at that vector address we have again written a second jump instruction to some label, and at that label the ISR is written. So this is how we manage with that addresses, right? So I said there is hardly 8 memory location gap. So what we normally do is, microcontroller is going to jump to this address. But what does programmer do? Write another jump at this vector address, and at that another memory location we write our ISR. Okay, fine. Now, whether that interrupt has arrived or not, we get to see on these flags IE0, TF0, IE1, TF1, RI, TI. Where are these flags available? These flags are available in TCON register and SCON register. So in timer control register, we have timer flags as well as hardware interrupt flags, int0, int1. And in SCON, serial communication control register, we have TI and RI flag. So just let me show it to you. TCON register. In TCON register, what do we have? The lower 4 bits of TCON were meant for interrupts, and the upper 4 bits were meant for timers. The lower 4 bits are meant for hardware interrupts. INT0, INT1. So the lower 4 bits, all of these 4 bits are related to hardware interrupts, right? And the upper 4 bits are related to timers, right? So when I say timer 0, timer 1, whether that interrupt has arrived or not, where do you get to see? At the flag bits. So TF0 is a timer 0 interrupt flag. TF1 is a timer 1 interrupt flag, right? So TF0 and TF1, right? The run bit is to start and stop the timer, okay? But then flag bits are whenever they are 1, mean there is an interrupt arriving from timer 0, timer 1. And now look at the lower 4 bits. IT0, that the 0 indicates INT0, 1 indicates INT1. So whether that interrupt has arrived or not, hardware interrupt has arrived or not, that indication is on IE0 for INT0, IE1 for INT1. Whenever interrupt arrives, IE0 bit will be set, IE1 bit will be set. Fine. And look into IT0, IT1. These 2 bits are going to decide the triggering signal of hardware interrupts. How are the hardware interrupts? Active low. Correct. So these 2, IT0, IT1, are going to decide the triggering signal. Active low means either falling edge or logic 0 level. Okay. So I have shown here IT1. See here. Look into the down part of the slide. Whenever that IT1 bit or IT0 bit is set, it means the hardware interrupts are activated by the falling edges. So any signal arriving, the falling edge of that signal is going to activate the hardware interrupt. And whenever that falling edge arrives, the respective flag IE0, IE1 is going to set. Fine. So IT indicates interrupt trigger, right? So if that IT bit is set, it means falling edge of the signal is going to activate the interrupt. And if the bit is cleared, IT bit is cleared, logic 0 level is going to trigger the interrupt. So either it is falling edge triggered or low level triggered, but active low, right? So that is decided by IT0, IT1. So from this you understand, whenever we are dealing with hardware interrupts, I need to use interrupt SFRs as well as I need to use tick-on SFR. Again, I repeat, whenever we are using hardware interrupts, I have to use the special function registers of interrupts as well as I have to use the tick-on special function register. And what is tick-on doing? Deciding the triggering signal of the hardware interrupts, and whether the interrupt has arrived or not, I get it on those flags, IE0, IE1 flag. Okay, but if you are using timer 0, timer 1, if you are using internal interrupts, I do not need tick-on, right? For serial communication, I need to refer SCON register. Hope you are getting me. So that tick-on is interlinked with interrupt as well as with timer. Right? So where are these available? IE0, TF0, IE1, TF1 is available in tick-on register. Tick-on.1, tick-on.5, tick-on.3 bit and tick-on.7 bit. And RI and TI are available in SCON bits. SCON.0, SCON.1. Is that okay? And what is the default priority on these interrupts? INT0 has the highest priority, that is 1. The next priority is timer 0, then is INT1, then is timer 1, and serial communication RITI has the last priority. So if all the interrupts, right, if there is a condition occurring, all the interrupts arrive at the same time, then who will be serviced? It is INT0. Is that okay? Or else if serial communication and INT1, if these 2 interrupts arrive at the same time, serial communication and INT1, then who will be serviced by microcontroller? The highest priority. INT1 will be serviced, right? So what is this priority doing? It is resolving the request that arrives simultaneously. Okay, and as well as this is the default priority, but the programmer can change the priorities with the help of IP SFR. Okay, so then we will look into what are the special function registers associated with interrupts. There are two SFRs related to interrupts, and that is IP, interrupt priority register, and IE, interrupt enable register. So from the name, see here, interrupt priority register, it is going to change the priority. Programmer can decide who should have the priority. The address of the SFR is B8 hex. It is bit as well as byte addressable. And IE, it is going to enable and disable the interrupts. Right? Now see here, students, whenever we reset microcontroller or whenever we power on microcontroller, all the interrupts are disabled. Correct? Not in use. We need to write IE control word, interrupt enable control word, to enable the interrupts and then use them. Correct? So IE is meant for enabling and disabling the interrupts. And by default, all the interrupts are disabled. Correct? Now, IE and IP both are bit as well as byte accessible.